Right, so let's talk about database indexing. So database indexing is the technique of making sure that we can optimize the access of data. Once we've stored it for permanent storage, we eventually want to be able to retrieve it as efficiently as possible. So database indexing is going to allow us to do that by calculating indexes that is going to allow us to jump directly to the records that we're looking for. So let's take a look at how that works. So as you might have seen in algorithms and other courses, right? The different algorithms performs different ways, right? Depending on how they're implemented, right? If you have just a one loop or you have nested loops, right? You can easily increase the performance or reduce the performance, right, by orders of magnitude, right? Depending of your search space that you're going to go through for looking for pieces of information. If the time that you take or the number of steps that you take is proportional to the number of elements, then we say that your performance is linear, meaning that if you double the number of elements that you're looking for, and the time that it takes you to find something also doubles, then we say that performance is linear. If instead, right, if you double the amount of elements, but the time and steps that you take to find something quadruples, right, then we say more than doubles. So if you double the input, but the time it takes you more than doubles, right, then that means that you're worse than linear, right? You might be even quadratic or cubic, right? So your algorithm, we're interested in knowing how your algorithm is susceptible to as the size of the problem increases. And we also saw that if you're clever, if you organize or you pre-process your data, you could have significant improvements in the algorithm of finding things, right? For instance, if you have a random set of elements, right, and you're searching for things, the only possible algorithm is to start at the beginning and work your way one after another until you find what you're looking for. But if you know that you can order your items using a particular field, then we know that if you're going to search by that field, and then we know that we can increase the performance quite a bit, right? Bring it down from linear down to logarithmic, right? We can dampen that curve. But that only works if you're going to search by that one key. Now there's an even better process or algorithm where you could that you can eliminate actually the search completely, right? If you know where things are, then there's no point in searching. Where is it? Well, where it's supposed to be. So if you know where you are, where it is, then there is no searching. And that's there's some algorithms, right, that you can use that mechanism, right, that everything in its place and a place for everything. And where could it be? Well, in the only place that it could be, right? And then you can find it in order one, meaning constant time. It doesn't matter how big your search space is; you're always going to take the same amount of time. That's beautiful. Our parents were correct when they kept telling us that they walked into our room and it was just a big mess and you can't find anything, and that if we would just organize things, we could certainly be able to find things. Now, oftentimes within that mess, for us, there was order in our heads because we knew where things were and there was no searching. Where are things? Well, here they are. It's kind of like the same arguments I have always with my wife when I'm looking for something in the fridge or for something in the closet. I can never find anything, right? And whereas she comes in here and she plucks it out and says, "There it is," because she knows how the information or the things that were stored in there. She has some kind of indexing algorithm, right? That she knows where she puts it, either by memory or she has one particular way of organizing. And it makes sense to whoever organized it, but it doesn't make sense at all if somebody doesn't know what was the organization principle. So that leads us to this first one, where it said where depends on how you organize it. it makes sense to the person who organized it. But the problem is that it brings this case, right? That you can only organize it in a particular way, right? For instance, if you imagine you had a phone book and somebody said, well, find me somebody with a particular last name, and now imagine that phone book was not sorted, right? It would be unfortunate, right? The only possible way that you can find anything in an unsorted phone book would be that you could start from the first page, right, and you go and work your way until you find, one at a time. You finish every one page, going to the next page, looking for the last name that you're looking for, comparing, and that's the search algorithm. It has to be linear. If the phone book is twice as big, it'll take you twice as long. But if you order by last name, then you can certainly use a much more faster algorithm. You could use binary search, right, where you start at the beginning, you start like in the middle, and then you work either left or right depending on the key that you're looking for. That certainly increases your performance. Instead of being linear, now you've tampered down that curve to be more like a logarithmic. But that's only true if you organize by last name and you're searching by last name. But imagine you didn't have a last name. Instead, you have a number, right? You have a phone number. But the phone book is not ordered by phone number, right? It's ordered by last name. So the indexing that you chose. Yes? Somebody had a question? No. The indexing that we chose that was the last name is useless because my search, I want to retrieve it by phone number, right? And since it's not indexed by phone number, it's not ordered by phone number, then I have to search. I have to fall back to linear search, right? I need to again search one at a time until I find the phone number that I'm looking for. So unfortunately, the organization. It's only useful if that's the search mechanism that we're going to be using. But actually, that doesn't stop us from organizing in both ways, right? We could have two versions of the phone book. One that is sorted by phone and one that is sorted by last name. And depending on how we want to search it, we could use one or the other. So the same principle is going to apply here in relational databases, right? We're going to, our tables, we're going to create indices on these tables based on the predicates, based on how we want to retrieve the data from the databases, right? If we want to retrieve it by last name, then we're going to create an index on the last name. If we want to retrieve it by phone number, we'll create an index on the phone number. And what the database is going to do is that it's going to leave the original database alone, right? The original records, it's not going to touch them. Instead, what it's going to create is a smaller copy, right? What we're going to do is that we're going to create a small copy of the original database, right? And which is going to have the fields by which we want to sort. Right? So it's going to organize, it's going to sort the content of the new table, right? Not the original table. It's going to leave the original table alone. It's going to create a copy, and it's going to sort it. It's going to organize it in a tree structure, right? In a hierarchical tree structure, a B tree. We'll see in a minute, and that can be searched, right, in a much faster fashion, much more than linear, right, in a logarithmic performance. And you can, the copy, the index version of the table is going to be a smaller version of the original table. It's just going to have the field by which you're indexing, plus is going to have just a reference of where the original record was, right? It's going to say, okay, well, I can find it once I found the index, right, that I'm looking for. Right, what I'm going to find there is not the original records, not the original fields. Instead, I'm going to find is a reference of where in the file system, right, what block, what file, what block, right, where actually I can go and retrieve the original record, right, and then I can bring it back into memory. And we can have multiple indices, right? One index on the last name, another index on the phone number. Both of them smaller versions of the original, right? Of the original table. Now we need to consider that there are different types of indices, right? You might be, if you're doing an index on the phone number, well, we know that phone numbers are unique, right? I have my phone number and you have your phone number, and there is no there's a guarantee that these phone numbers are unique, right? They're tied to you or me. But whereas last names are not necessarily unique, right? I might have a last name. All my family has the same last name. There's a whole bunch of people in the United States that are also enunciados that I don't even know, right? And they all have the same last name. So certainly some indices are unique indices, and some indices are not unique, right? And that's very important because the overall performance of this strategy is heavily based on whether the index that you're creating is a unique index or a non-unique index. Let's take a talk about that a little bit. So let's take a look at first how we create the indices in SQL. Right, the way we do that is using the create index function or operation, right, where we say create index, we give it a name, and then on the table and the field that we want to create it. So for instance, this would be create index phone number on the contact table, and the field is phone. Okay. So for instance, here we are creating an index on the on a student table. And student table, if you remember, it had a primary key for the ID of the student, and had the major ID, which was a foreign key that was connected to the departments, right? And so here we're creating an index on the major field, right? And a common name is to create append the underscore IDX index at the end of the index that we're creating. So that will create an index, and you can create any number of indices, right, on the same table, right? So for instance, here we're creating another index, and this is a unique index. See that? Notice that the first one, this major ID index, right? This is not a unique index. If it's a foreign key, you're going to have the value of that foreign key repeated multiple times, right? Because you might have 1,000 students that are in the same college, right? Are in the same department, right? So this major ID, this foreign key, is going to repeat multiple times, right? So it's not going to be a unique index. Whereas we know that the student ID, we know that is a primary key, and obviously it has to be unique. So we can create one and say create unique index and student ID on that same table. Yeah, so there are two different types of indices. One is a unique index, and the other was a non-unique index, right? We've created a unique index on a unique field, like a primary key, and here we created a non-unique index on a foreign key, such as a major ID. And we'll see that the performance on one or the other is heavily impacted on whether it's unique or not. And also, it's heavily impacted on the this non-unique index. What is the ratio of how many records are referenced by this foreign key with respect to the overall records, right? If there's a the more with the higher ratio of how many records are referenced by a non-unique key compared to the overall keys, right? The higher the ratio, right, the less performance you're going to have, right? And actually, it could start actually being worse, right? So, for instance, if you have lots and lots of colleges or departments compared to the number of students, where maybe you could have 1,000 students per department, as opposed to you have very few departments and lots for the same number of students, where you have many more students for the same number of departments, right? That would heavily impact the performance if you're going to use this non-unique index. Even actually getting worse performance if you're using non-unique indexes, as opposed to if you didn't have the index. So usually when we create indices, we think that just by creating the index, we're just going to improve the performance. Not necessarily. We have to make sure that the ratios are right for the indices to work. In particular, non-unique indexes. Unique indexes are always going to improve performance when we do unique indexing, right? But non-unique indexes, we have to be careful, and we have an example for that. So here's this graph illustrates the use of unique indexes and non-unique indexes on a sample of a couple of records here. So we have 10 records here for Joe, Amy, Max, Sue, Bob. So these are 9 unique students, and spread over 3 different departments, right? So we have 2 indices, one on the primary key, student ID, and we have the another index on the non-unique key of the major ID. If notice here that on the left-hand side is the unique index. Obviously, one of the index refers to one record. There's a one-to-one mapping between the index and the record that it references, right? But in a non-unique index, you see that we have evenly split, where each index is actually referencing 3 different records, right? So these are referencing 3 different records, right? The 10 over here references Joe, references Max, and references Lee, whereas this 20 references Amy, references Sue, and references Kim, right? The bigger the ratio of how many, the more these non-unique indices reference the original records, the less performance you'll get. And you actually get worse performance, right, if the ratio is too big. So we'll see that in a minute.